Welcome back, everyone. We are starting chapter 6 here, and we're starting with composite functions. Basically, what a composite function is, we are putting a function inside of a function. And the best thing to do is to view this as we're going to work our way from the inside out. That's going to be a much better way of doing that. So this is pronounced f composite g of x. That is not times x. X is the domain of g. And g of x, its range, is the domain of f. Try to sort that out. I'm going to save a little bit of space because I'm going to need a little extra for these down here when we get there. So let's start with part A. We have our two functions here. F of x equals 3x squared plus 5, and g of x equals x plus h. That is going to be a recurring theme, that x plus h. Let's be moving on to calculus. So here we go. F composite g of x is f of g of x, which means this is f of x plus h. And what that is going to mean for us is I'm going to now go to the function f, and I'm going to replace that x with the x plus h. So this is going to be 3x plus h squared plus 5. And we could FOIL that out if we needed to, but for our purposes, this is fine. Part B goes the other way, g composite f of x. So f of x is 3x squared plus 5. And I'm now going to replace that x there with this expression. So it's going to be 3x squared plus 5 plus h, or just 3x squared plus 5 plus h. H is actually a constant for our purposes. Now, for these, we left it in terms of x, as functions of x. We can also do these composite functions as and evaluate them at specific values. So let's start with A here. And here we have our two functions f and g. So this is f of g of 2. So what I'm going to do is I'm going to evaluate g when x equals 2. So f of, this is going to be 2 squared minus 2 times 2. This becomes f of that's 4 minus 4, that's 0. So this is f of 0. So now I'm going to evaluate f when x equals 0. Notice these up here ended up being functions because we had a generic x, and these are going to be specific numbers as we're looking at them. All right, so let's do part B. This is now going to be g of f of 2. So I'm going to evaluate the function f when x equals 2. So g of 2 times 2 plus 3. This is going to be g of, that is now 6 plus 3 is 9. That's 4, pardon me, 4 plus 3 is 7. I'm now going to evaluate the function g here at 7. (49 minus 14, 35). Part C. So we're going to do f composite f of -3. So I'm first going to evaluate the function f when x equals -3. So 2 times -3 plus 3 is going to be, that's -6 plus 3, that's -3. So f of -3 is now 2 times -3 plus 3. 6 plus 3 is negative 3. Not too crazy. And part D, we're going to do G composite G of negative 1. So I'm going to evaluate this at negative 1 squared minus 2 times negative 1. That is going to be G of 1 plus 2. It's like G of 3. So now I'm going to evaluate G again when x equals 3. So that's 3 squared minus 2 times 3. 9 minus 6 gives us a positive 3. That's not too bad. Next up, we're going to talk about the domain of composition functions and then some decomposition. We're going to break it apart. All right, so the domain here, the domain of f composite g of x is the set of all x's in the domain of g such that g of x is in the domain of f. So let's look here. I need values of x that are going to work, that are going to get me values of y values of g. So that actually is going to be, the domain here is going to be the x values here, 1, 7, 9. And I'd like to point out that if I use the domain of g, the range of g, 3, becomes the domain of f to give me 20 and so on. All right, example 4. First off, I'm going to notice for f composite g of x, an x value that is not in the domain of g, x cannot be negative 4. Otherwise, we're going to have an issue. However, when I composite this, so f of g of x, this is going to give us 2 over 1 over x plus 4 minus 3. And I'm going to multiply the top and bottom by x plus 4 over x plus 4. And that's going to give me 1 minus 3 times x plus 4. The numerator doesn't matter. I need to find out what value in the denominator here is going to give me a problem. So this is negative 3x minus 11. So it looks like we're going to have a problem at here. So here are the two values that we are going to have to avoid. And negative 4 is going to come first. So here we go. It's going to be all values up to negative 4, excluding negative 4, to negative 11 thirds, excluding 11 thirds, negative 11 thirds. That is our domain of interest. Basically everything but these two values. State the domain of the composite function. So we're going to start out for sure, x minus 1 has to be bigger than or equal to 0, or x is bigger than or equal to 0. So that's definitely going to limit us on our domain. However, when I composite them, so now I'm going to put that into there. Now the radical and the squared cancel each other out. And there are no restrictions with something like this. So our only restriction in this case is going to be 0 inclusive. Oh, 1, I mean. 1 off to infinity. Yeah, you have to add the 1. All right. So this next part isn't too complicated. we're going to go in the opposite direction of a composite, and we're going to do what's called a decomposite. And to be clear, I've removed this one down here. All right, find the functions f and g such that f composite g of x equals h of x, and h of x is here. Here's the easy way to do this. Get what's under the radical and make that your g of x. That makes f of x root x. And you can see when you put g of x into there, you get h of x. Not super complicated. 7 is very similar. I can see the x plus 3 squared, x plus 3 squared. So what I could do is let g of x in this case is going to be x plus 3, meaning that f of x is x squared plus 5 over 7 minus x squared. We could have let g of x be x plus 3 squared, and then we would just have x plus 5, 7 minus x would be the same thing, but I think this makes it a little bit easier for us. So this one's not so complicated compared to certainly chapter 5.